Okay, so uh, when it comes to fluoroscopy and the registry itself, we can break down fluoro into sort of conventional fluoro, which uses an image intensifier tube, and the flat panel detector digital fluoro. Pretty much either one that you use now is still digital in that information is kind of turned into ones and zeros and then processed by the computer, and it could be displayed on monitors, and it can be recorded digitally and then looked at frame by frame, etc. But when I say conventional fluoroscopy, I'm talking about an image intensifier tube, which we're going to go over in great detail in a few minutes, versus the flat panel detector, which is what we'll talk a little bit more about in our last true lecture on Wednesday. Um, Ultimately, though, what's interesting for me and you is it's really only a matter of time before they take conventional fluoroscopy off of the registry, and then we won't have to teach it because more and more departments are moving towards the flat panel technology, especially when it comes to fluoroscopy in the OR with the C-arm, which we talked about in the lab, and I showed you some of the videos, and fluoroscopy as used in an angiographic suite, for pacemaker placement and angios work. That's all going pretty much flat panel. But we still have an awful lot of image intensifier tubes used in regular radiography for things like GEs and the occasional barium enema. Both of these exams used to be quite common, and departments rotated people through fluoroscopy um, for hours in the morning. Usually wasn't something done in the afternoon because the preparation for patients required them to be NPO, in other words, not eating anything. So it's not nice to schedule an exam at 3 o'clock in the afternoon and expect someone to not have eaten from maybe midnight the night before. But until the registry takes this off, it needs to be covered. And there's still a significant amount of them out there to do so. But I'm seeing less and less in the next few years as departments replace equipment um, and as some of those parts and manufacturers don't want to uh, continue to do maintenance on those types of systems. And you'll see that the images are much better in digital fluoro use of a flat panel detector. Um, so that being said, radiation amounts to patients going down, and the other reasons to use flat panel detector technologies is really going to ultimately push out the image intensifier systems. However, let's do our lecture on it because for the next few years at least, I'm sure it'll still be covered on the registry. So the rationale, as you probably know, is to kind of put motion into these usual static radiographs. And that allows us to watch the flow, for example, of barium through the esophagus into the stomach. Um, so there's a power in seeing something in motion. Certainly, if you're looking at contrast going through a vessel. But believe it or not, it comes back to Thomas Edison, who introduces the first fluoroscope back in the late 1800s. So again, we're looking at anatomy and motion, and that can help, allow us to see structures and functionality that we might not see on just a plain static image, right? It might be hard to realize that someone has an esophageal disease that makes it hard for them to swallow if all you're taking is a static image versus watching flow actually go down. So here is a very old picture. One of the issues with fluoroscopy from the beginning is that the image was always very dark, and you had to do a lot of different things to make that image brighter, which is where we get this term to even begin with in terms of image intensification, right? Another way we can look at that is brightening up the image, right? Intensifying the image. Uh, so uh, to work better in the dark, right? Some of the physicians would wear these kind of like red goggles that allowed them to see better. I remember the lights were turned, if not entirely off, down to the dimmest amount that they um, image intensifier tube above this. But in terms of what we do, we would often assist. We're doing less and less of that now. But we would mix up the barium, assist the radiologist or whoever the fluoroscopist was, hand them cassettes if they were going to do reason for us to be in the actual in matter in the colon. Exams, those kind of things. And we had to essentially be around for the entire procedure, even if it was just right outside of the room. Of course, we also have to set up uh, the exposure technique and set up for fluoro. So a little bit more on that in a second. Hi, Iman, if you could just mute yourself, getting a little bit of feedback from you. Okay. So as we've seen, right, fluoro is being used all over the place, right? It's not just used in the diagnostic department, but it's being used in cardiology, so cardiac cath. It's being used in special procedures, so angiographic rooms, and in the OR. All over the place. You can tell here, it might be a little bit small on your screen, but this is actually a detector. See the uh, image of that there. So it's really, there is nothing else really that can be used to image uh, blood vessels in much of a dynamic way, other than maybe ultrasound, maybe perhaps in MRI, can we actually see something in motion. So in a conventional room, right, we have a room similar to this at the school, right, and there is an overhead fluoroscopic sort of console, right? So we have our image intensifier encased in here, and we're going to break down the image intensifier tube in a few moments. Design, like it says in number 1 here, is to convert the X image to a visible light, and to make that image brighter and smaller for us to look at. We're going to see that there are a couple of things that go into the actual increases in brightness. And then we take those couple of things and put them together to kind of figure out what our total brightness is. And that image should be displayed on a monitor for whoever's fluoroing to look at it. And that monitor should, another set of monitors should be outside. So hopefully the technologist does inside, risking exposure to radiation. Now, interestingly enough, right, so this is what you want to take note of, is the MA is very low, right? We're talking 0.5 25. So you may have heard that fluoro gives you a lot of radiation. If you just look at the MA, you would be like, no, right? MA is usually in stations of hundreds, right? 200, 300, 400. This is at most 5, right? And KV, typically the KV is higher, right, at about 100 or so, and that's to penetrate the barium. But even with a higher KV, which many would argue leads to a reduction in overall mass, you might think, why is this exposure to the patient so low? It's that the exposure is ultimately very high because remember, mass is the combination of MA and time. And while the MA is very low, the time can be incredible. There's an alarm that goes off not after a few seconds, like the alarms that we have built into regular systems that turn off, give crazy sounds that you hear in the lab. We have an alarm that typically goes off after 5. That's an awful lot of time. That is way CAT scan. Compared to the fraction us. And now we're talking about an alarm going, you've hit the 5-minute mark, and then that doesn't mean, oh my goodness, you stop. That means you just take note that, gee, you've used a lot of fluoro, and then you hit the reset button and allow the physician to continue to fluoro. So the exposure to the patient and potentially occupational exposure is not due to MA, it's due to an incredible amount of time. And there's really not a lot of ways to get around that. Aside from the expertise of the radiologist being able to do things in literally less time, all you can really do is use what's known as intermediate fluoro, or fluoro that kind of flickers on and off, but it turns on and off so quickly that the image doesn't lose resolution, or the fluidity of the movie, so to speak, doesn't look choppy, yet the generator is turning on and off the radiation so quickly that it reduces a little bit of the radiation, but still a lot of radiation in fluoro. Can't get around that, unfortunately. Let me go any. There we go. Before I continue, anyone have any questions? I didn't really go over the diagram too much. Hopefully you've been in fluoro or seen it a little bit. Anyone have any experience in fluoroscopy in the department? See a lot of no's. Yeah, it's not really the kind of thing that you get into really in the first few weeks. Um, I know I would try not to rotate students there right away, um, but you will. It's not going to go away, and we'll get back in there. Um, did some barium at St. Luke's. Okay. Um, yeah, and the question I'm asking is also difficult because as we're seeing more often, a lot of these cases are no longer being done fluoro, right? The barium work, barium enemas in particular, are being done more often in CAT scan. Um, so yeah, we're seeing what's left is we're seeing small bowels, we're seeing esophageal studies and GI studies. Now, what you might think that's pretty interesting is we know that the body is made of different thicknesses and different atomic numbers. So how is it possible, for instance, to follow the barium from something that is relatively not that thick, like the esophagus and the neck area, down into the thorax that gets much thicker, and then uh, from there into the abdominal area, where, of course, a lot of body fat there is getting much thicker. How do we maintain the brightness in our image, and how do we maintain the overall exposure, right? I mean, it's kind of hard to set technique that fast unless you're, the Flash and you can do things um, faster than anyone can notice, right? The system has what's known as ABC or automatic brightness control. So this is built into the unit. It's pretty cool. It has the ability to actually adjust the MA, right? Increase or decrease the MA, or the KVP as you move that image intensifier from an area of thicker to not as vice versa. And this is going to happen in real time. Sometimes you see a little bit of a blur as the fluoroscope is moving from one area to the next. And I would have demonstrated this to you in the lab. It's the only time I kind of subject myself to a little bit of radiation. But the ABC unit is somewhat similar to automatic exposure control, right? In that it can adjust instead of the time, really, it can change the MA or the KV. So this intensifier tube has a lot of steps to it. It's not terrible, but maybe because I've gone over this many times over the semesters that I've taught this course. But I'm going to run you through it. And this is a diagram not from your book, the internet, but they should be all pretty much the same. And I'm kind of give you an overview before we run through it step by step, right? You have this thing that kind of looks like a milk bottle. Uh, and similar to an X-ray tube, there's a cathode side where the X-rays are on the left over here, and then there's an anode side where you see the light coming out. That is our end process, or end material is light, and we start off with X-rays. And then what you see is there's going to be a number of conversions, right? We have this window followed by an input phosphor. The input phosphor is going to take X-rays and turn them into light. And at this point, you might say, what do you mean it's going to turn it into light? Isn't the light over here? So there's going to be a conversion from X-ray to light. But then we're going to convert, instead of finishing at this first step, we're essentially going to take that light, put it through another phosphor known as the photocathode. It's going to turn that light into electrons. Lots and lots of electrons. Those electrons are going to speed across the tube, and they're sort of by these things called the electrostatic lenses. Sorry, that thing on the bottom keeps popping up. Sometimes, so electrostatic lenses in this diagram is the same as electron optics. But those electrons are going to be powered, again, with KV, very similar to an X-ray tube, right? We have to create that potential difference. Those electrons will smash themselves into what we output phosphor, which is yet another phosphor that's going to now turn those electrons into a lot more light than we had after the process of the input phosphor, the one that's in yellow on the left. And that's essentially how it works. So I'm going to tell you all this again, but we'll go into a little bit more detail, and we'll kind of pop back and forth between this image, this slide, and the next few slides, right? So essentially, though, that light is going to be sent, so that output light in purple goes to a video camera, or in a digital system, a charged coupled device, CCD. We'll see another diagram where I'll point some of these things that happen that are kind of on the other side of the output phosphor. Start at the beginning. So you have your X-rays. They're coming in many cases from underneath the table through the patient. So if the patient's supine, they go through their back, so kind of PA, come out, and then are by the cathode portion of the image intensifier tube, right? And they interact with this input phosphor that we see, and it is usually made out of cesium iodide. Please pay attention and make atoms of the phosphors. And that's going to convert it to a light image. But again, that's just the tip of the iceberg here, right? We still have a few changes to go through. So in the second step, right, the light from the input phosphor is absorbed photoemissive material in what's known as the photocathode. The photocathode is a combination of antimony and cesium, and it's responsible for taking the light and turning it into electrons, right? So that's happening right in this blue area. And you see these two are sandwiched right next to each other. We go right from input phosphor to photocathode. And that is going to take our light image and essentially turn it into an electron image. And those electrons are going to fly through on their way to the output phosphor, which is much, much smaller. The output phosphor is made out of zinc cadmium sulfide. So here's our output phosphor. We can see it's much smaller than either the input or the photocathode. Okay, let's keep going. So that's going to convert it to a nice, small, bright image. Now back to phosphor. The input phosphor's diameter can actually change, right? So you might have a 6, a 9, a 12-inch diameters, and those are used to magnify and increase spatial resolution. It's kind of counterintuitive to what we've learned in the past. So we'll get to that in a few minutes. And in reality, the diameter kind of is what it is. What I mean by that is this doesn't iris like a Star Trek movie or something. It doesn't change. However, the voltages that are applied by the electron optics, so these little green dashes, can focus those electrons and make that narrow or more wide. And in a sense, that change of this stream of electrons that's going across that you see as kind of the dashed yellow lines here is what will change when we say the diameter of the phosphor. The actual input phosphor doesn't change, but it helps to think of it as it does, right, in our minds. So number 3, approximately each 60 kVp photon is converted to 200 photoelectrons, or essentially electrons, by the photocathode. And they're going to travel across, like we said, to the output phosphor. That pushing of those photoelectrons is going to happen by our electrostatic focusing lenses. They give out a positive charge, will repel essentially negative electrons, so we can push them forward from input to output phosphor, but we also have the ability that they're on both sides. We have them up here and on the bottom. That allows us to change the sort of diameter. I don't know if it's exactly a circle, so diameter might not be firm, but it'll squish them more together or less together. So they have this positive charge applied to them to do that. And when stream of electrons, and we call them photoelectrons at this point, narrow, that is going to cause more brightness. It's kind of like taking a hose with water in it and compressing it and squeezing it down, and suddenly the pressure of that water coming out of the tip of the nozzle is going to be much higher. So we call the brightness that is created from this type of squeezing down electrons by those charges coming out of the electrostatic. Believe it or not, I think I said that all correctly. Catch me on the video if I make a mistake. This is known as minification. As a matter of fact, it's known as minification gain, G-A-I-N. It's the increase in brightness that you get from a compression, right, of your photoelectrons. Um, Now, number four, the accelerating anode is designed to attract electrons from the photocathode and accelerate them. The fact that we apply 25 to 30,000 volts, for us, that doesn't sound like that much. It's just 25 to 30 kV, but it actually is, as all X-rays have a lot of voltage, even a finger, right? So when we say anode, again, just to show you what we're talking about, it's this side of the tube. So the anode, the main portion of the anode is the output phosphor, but I guess we could include the output window as well. You guys, stop me if you have a question. So the anode, right, is going to pull in those electrons to the electrons being pushed in by the electrostatic lenses. And then they're going to hit this output phosphor that is made out of zinc cadmium sulfide. And now that's going to convert us into lighting. But the ratio of the number of light photons emitted by the output phosphor is much more that came from input phosphor. And this conversion, due to the fact that we pump in a lot of energy into this, a lot of volts, that is known as flux gain. So we have two systems that are going to ultimately tie in together. Actually, it's the product. So we're going to multiply the minification gain times the flux gain. That will give us our total brightness gain. And we're going to see that in the slide. Mention it in advance because that's what I tend to do. Then that light ultimately from the output phosphor, so this now called intensified image, passes through some fiber optics. It either goes to something known as a charge coupled device or another electronic chip known as a CMOS or complementary metal oxide semiconductor, as well as a camera, because we want to capture the image on the screen for the physician to look at, but we also want to capture the digital components of the image so it can be and looked at later, as sort of a movie, which we commonly call cine, C-I-N-E. So here is that another image, also not in your book, but it has a lot of the same components. And the reason I really kind of stuck this one in here is because now we get a sense of what's going on after this output phosphor. And you can see here there is a mirror that's set up kind of at an angle, allowing some of the light stream, intensified light, to go into the video camera or CCD, or as we've talked about in the past, to turn it into digital image, it goes through an analog to digital converter. Right? There might be another switch in here because usually ADCs work off of voltages versus light. But you see this mirror allows for a split. So as mentioned, some of it's going to go to the video camera or CCD, and another portion is going to go towards a source that might take us to the monitors inside the room and outside of the room. So we can kind of look at this portion going to the computer and this portion going to the video monitors. But this is a nice image because it kind of shows us everything happening again, right? We have our input phosphor sandwiched with our photocathode, so light turns into, X-rays turn into light, light turns into electrons are streamed across and narrowed by these focusing electrodes or electrostatic lenses, right? You see them referred to a couple of different ways. Um, as they reach the anode area of the tube, right, they reach that exit or output. And you can see here that we're getting around 5,000 light photons, ultimately for every original X-ray photon. Right? We have to go through a number of conversions to get there, right? And we have to pump in a lot of energy to do this. And we still want it to be fast enough so that we can see the image on the screen without a lot of lag. So to reiterate what I was mentioning before, right, we have what's known as minification gain. That's part of the brightness. So the minification gain is the ratio or the difference. So let me just give you the sort of direct definition and explain it a little bit. The ratio of the square of the diameter of the input phosphor to the square of the diameter of the output phosphor, right? And we see the formula down below here. Magnification gain typically gives our output image 35 to 80 times more brightness than the initial input image, right? And it's due to the size of the input phosphor compared to the size of output phosphor. So we're talking about going from 6 to 12 inches down to about an inch. So 6 to 12 inches here on the input phosphor to maybe about an inch of the output phosphor. So we're comparing this one, this one. The other type of magnification, I'm sorry, brightness that goes in overall brightness is what we call as the flux gain. Right? And remember, that's going to be combined with the minification gain to give brightness. So the flux gain is the number of light photons at the output phosphor compared to the number of X-rays at the input phosphor. And this is not about going from large to small, right? That was minification. Flux gain is the fact that we applied the voltages and we created the electrons, and all of those conversions that happen there related to energy that give us a much higher number of light photons than what we started with in terms of X-ray photons or the initial light photons from the input phosphor. So our flux gain in form of a formula is simply the number of output light phosphors compared in the denominator to the number of input X-ray photons. So that happen in the X-ray, the light, the photocathode that produces our photoelectrons, the energy that is applied here to change those and accelerate our electrons towards the output phosphor. It's not just about the fact that the output phosphor is smaller than the input phosphor. So flux gain is different than the power of the two that total brightness. So here you go. Total brightness or brightness gain, if you want to call it that, is the minification gain multiplied by the flux gain. And all together, we're talking about a 5,000 to 20,000 increase, especially when it's new, before things start to degrade with use. And we don't really have to get into changes in terms of time. Now, how can we measure this brightness gain? way to measure it. So we have total brightness, which we magnification multiplied by flux gain. Um, but another, probably more accepted way is to look at what we call the conversion factor. So the conversion factor is the accepted measurement um, to look at how much brightness was actually created with the use of an image intensifier. So this is not on the test, don't worry. But it's the ratio of the output phosphor compared to X-ray exposure. So conversion factor is going to be candela, which is a unit of brightness based on candles at one point, uh, squared the Rankins per time per second. Now, use of, although at the end of the day we do have a vast improvement in brightness, it's still a rather inefficient process, right? We have many, many different conversions. I mean, just look at this here. X-ray energy converted to light energy, that's at the initial input phosphor. Then this light energy is converted into electrons, as we said, that's done by the photocathode, which is kind of sandwiched right next to it. Then these electrons are again converted into light, albeit a lot more light than we started with by the output phosphor. But even then, we're not really done because that light has to be converted into electrons so that it can work with a TV camera. Um, and those electrons, again, have to be converted into light energy to show you analog grayscales with significant brightness on the model. Looking, there's even more conversions, as mentioned, when we get into the digital world that happen through use of a digital converter so we can get that information, that light and that electrical signal ultimately into ones and zeros, right? Like CAT scan, sounds a lot like what we do in DR and CR, right? A lot of versions near the end, but fluoro has even more fluoro because of the initial conversions that happen within the image intensifier unit. So now we're getting into a few smaller kind of items. These image intensifiers have what's known as magnification modes. Um, and the magnification mode is essentially changing the diameter of the input phosphor. So we mentioned this a little bit earlier, and we said that the actual diameter doesn't change, but it's the amount of energy or voltages that are applied to those electrostatic lenses that kind of run across the top and bottom of the tube, kind of on the sides over here, that you can see will have an effect on the beam of electrons that are making their way from the input to the output phosphor. And essentially, it's not as intuitive as what we've learned. Uh, Units that have magnification are known as multi-field or dual field intensifiers. And when you magnify the image, take note, is not what we usually say. Usually magnification makes spatial resolution worse. However, in the case of fluoroscopy, when we magnify the image, the spatial resolution. However, the major trade-off in red in the first paragraph is patient doses go up 2 to 4 times. Magnification mode. So a lot of these units are not on and off. In other words, turn on, magnification, turn off. They have different diameters, I should say. Excuse me. And by a parameter known as the multi-field. And it's when we reduce that number, it causes an increase in magnification along with an increase in dose to the patient. So if we go from, this is not the best example, if we go from 9 inches going down, that will cause an increased magnification. So better spatial resolution, but also more dose. Anyone have a question on magnification mode, kind of how that works? A little bit counterintuitive, what we've talked about. Okay. So automatic stabilization of brightness. Brightness level at the monitor must be maintained throughout the examination. This is another system to help us keep the brightness level at the monitor. Not that important to go into any more detail on that. Fluoroscopic technique. So the hard part is essentially over, right? We talked about how X-rays turn into intensified light, right? And the various phosphors. So make sure that you understand the process from A to B, and then the different conversions that happen within there. In terms of fluoroscopic technique, it's usually pretty high, right? You'll see from the top 3 are all in this 110 to 120 range because they all generally include the introduction of barium sulfate into the patient, right? That's that chalky liquid that you mix up, and sometimes there's a thin version and a thick version. And once upon a time, I like to tell the story, but I won't give you the full story of where I had a GI, but they had flavored barium. So mine was strawberry, and I was even able to get them to refrigerate it for me. This is when I was still a student, though. So how nice were the techs to me as a student? Thank you. Shout out to Lawrence Hospital in Bronxville. And then as we don't have a very high atomic number for everything else going down, you don't need as much kilovoltage for air and abdominal use and so on. And we go even lower if we're using fluoro in, let's say, angiographic procedures where you're injecting contrast media, like in the case of a myelogram, for example. And certainly much less for extremity work and joints, right? Fluoro was commonly used to look at joints like within the knee, within the shoulder, in the hip. So lots of use for fluoroscopy. Very, very common technique, and used pretty much all the time in the world of pain management. So if you ever go to a pain management center and they talk about getting an epidural, that's usually done under fluoroscopic guidance. Usually done with a C-arm versus an entire fluoro unit like we've been discussing, but still within the fluoroscopic world. So the image quality could be better, especially now that we can compare it to flat panel technologies, right? But essentially the number of X-ray photons absorbed by the image intensifier, right? So how many X-rays are actually absorbed are all going to determine sort of the mathematical or statistical quality of the image. This is a fancy way for saying we still need to use a proper technique to penetrate the part, and we still need adequate intensity, enough radiation to begin with for this system to work. So we're not going to have any intensification, right? So no form of intensification can improve the image unless we provide enough photons and radiation to begin with. In other words, enough absorbed photons. Because if we don't have enough, our resolution could go down. Scintillation, which is the process of taking an X-ray and converting it to light, will not be as efficient, and our contrast and distortion overall, and we'll talk a little bit more in the next couple of minutes near the end of this presentation already on some of the issues that you have with fluoroscopic images. So a scintillator is any type of phosphor. So we find this in the input phosphor that can take light, take X-rays and convert it to light. But you can have some issues. Not every scintillator material works as well. Over time, the phosphor can be degraded, and that turns into kind of noise, right? Kind of the similar noise that you get if you have photon starvation or quantum model where you don't have enough radiation. Our contrast, right? So to talk about this a little bit, X-ray photons that do not get absorbed by the input phosphor. So this is not a problem of having enough quantity, enough intensity. Some of the photons of X-rays just don't make it into the phosphor, right? Or they go through the phosphor, right? Which is kind of interesting. They don't actually interact with the phosphor, go through the phosphor. They're like passing by those electrons in the image intensifier tube and actually hit the output phosphor. Right? Remember, it's supposed to be a stream of electrons hitting the output phosphor, not an original photon that was able to get past the input phosphor and maybe even past the photocathode on its way out. And that's going to cause an overall decrease in contrast. So in a second situation that can hurt your contrast, so the title of this slide should be, things that can happen that cause contrast to go down. The light photons generated by the output phosphor, instead of going into your CCD or CMOS chip or the camera or getting to the mirror, can actually go backwards the other way and interfere with the stream of electrons that is still coming towards that output phosphor, causing sort of random electrons that will decrease the image contrast rate. So it can change things there. So these are things you can't really do anything about. A couple other things that you can't do anything about is what's known as pincushion distortion. So the input phosphor is curved. Right? And if we go back a little bit, I guess we can see it here. Can't really see it from this angle. Right? So this is curved, right? But the output phosphor is a square. So you've heard that expression, trying to put a round peg into a square does not work that well, right? So the fact that the input phosphor is curved and the output phosphor is a square, we're going to have some slight magnification issues at the edges, such that we get this kind of distortion, right, where our lines aren't nice and crisscrossed, which is what we'd like to see. This completely goes away with digital fluoroscopy utilizing a flat panel detector. Veiling glare is another issue, right? Contrast is reduced in the image, caused mainly by light being scattered. So just like X-rays, light can also scatter. So in this case, scattering at the output phosphor, excuse me. and that's going to cause some reduction in contrast. Another one, vignetting, is again kind of based on just the construction of the image intensifier tube such that it's brighter towards the middle of the image. And as we get to the periphery, as it says here, we kind of lose the brightness. Again, not much you can do with this situation. Now, the fluoroscopic units themselves. We can take conventional, in this case, to mean the fluoro carriage at the top where you put your arm on it and kind of move it all around, right? That we're kind of used to. It's this, sort of rigid, fixed carriage that they call it sometimes. Or we can have a unit that we don't have at the school, known as a remote fluoroscopic unit. So here's our conventional one. This is kind of what we're used to at the school. Notice that the person doing the fluoro is inside the room, has to actually operate everything here. And as we saw in the lab, all the different knobs and little mini joysticks and whatnot are there to move the tabletop from front to back and all over the place, even turn the entire table up. But all that is done from inside the room with an image intensifier that is on top of the patient, meaning that the tube is underneath here as we described at the very beginning of the lecture. Now, a remote fluoroscopic unit is the opposite in many ways. One, the image intensifier is down here with the X-ray source at the top. And why do we call this remote? Is that we don't have to be in the room. So patient is brought into the room. At that point, we're there, we set them all up. But then from outside of the room, and this is done to reduce radiation to people who are fluoroing, so this was a good idea. We can control everything from essentially a similar type console outside of the room. The only problem that you have here, which is why at the bottom of this sort of paragraph it says it might not be suitable for every exam or patient, is because it's kind of hard to tell patients to oblique themselves, right? So there has to be an understanding. The patient has to be cognitive enough, both either mentally and or if there are language barriers, for example, this would not work very well, or simply if the patient is physically unable to assume certain positions without your help, in which case you have to run in and out of the room, and that kind of defeats the whole purpose of it and kind of slows down how this procedure would work. But in a good circumstance where a patient is able to comply and understands and can move around and can, drink the barium or whatever they need to do without you kind of holding the cup and, keeping the straw in their mouth and all the things we had to do, this is a nice setup, right? Of course, there's amplification so that you can communicate with your patient through an intercom system, etc. So that's what we mean by remote fluoroscopy. But also remember a big difference, again, is the image intensifier is underneath the patient. So how do we protect ourselves in fluoro? Well, the best way is not to be in the room, right? And we're seeing that more and more often. But if you are in the room, you still have to practice our standard protection. So distance, shielding. So distance, we want to be behind the person doing the fluoro, right? Because the other assumption is shielding. Everyone has their apron on, so you're wearing the shield, you're behind them, but then you want to be as far back as you can, putting in a weird way, right? The person doing the fluoro is another barrier for you as the technologist if you have to be in the room. Again, some of the older units, and I don't think we're really doing this anymore, they used to have these spot film slot covers, but inside the actual cover, so like you see this kind of gray or black line here, a lot of them are kind of missing anything behind that, but that used to be a slot Um, Kind of reminds me, yesterday I was uh, copying information onto a micro uh, SD card. And I had to put that micro SD card into a little adapter, but then I took that adapter and I put it into a square slot on my PC. But now imagine that this was actually a 9-inch by 9-inch square X-ray cassette. And we used to have to hold the cassette behind us. And when the radiologist wanted to take what they would call, naturally, a spot film, you would hand this to them or put it in because it only took one at a time. Right? This has essentially been replaced by several systems and now is probably completely gone. But they would cover that area, and then you would also have a lead curtain that would be at about waist level, right? Because remember, in a conventional system here, the image intensifier is like shooting X-rays up, so they're coming from kind of literally under the table here, and any scatter that kind of comes out of the screen that you're looking at now, essentially towards the fluoroscopist, um, can be nullified or reduced, at least with the use of this hanging lead curtain. And there were also lead gloves if you actually had to put your um, hand inside here. Why might you do that? Um, in order to get the patient into the correct position, the uh, physician or whoever's doing the fluoro would commonly have to literally move the patient's hips or turn things, um, and they could easily get their extremities into the beam. Not good. So typical exposure values are as follows, and I would express that you look at your book to get some more information on this. There are certain regulations. I don't know if they have quite changed that require a certain tabletop skin entrance exposure that based on this slide, which is probably maybe a couple years old at this point, was 2.2 Rankine per minute. I know I don't believe these have changed, so definitely commit this to memory. Hint, hint. 12 inches for mobile equipment. In other words, you can get a foot to the patient. Go any lower than that, and it's too much radiation to the patient. So minimum source to skin distance, right? So you could be at 13, 14, 15 inches. That's okay. But with mobile equipment, you can get as close as 12 inches. For stationary systems, like what we saw right up here, that um, can only go down to about 15 inches. As mentioned, we have this alarm that is set at 5 minutes. Hopefully, you use a lot less than 5 minutes, right? And it's actually 5 minutes of fluoro time. The procedure can last 20 minutes, but you might only use a minute of fluoro, right? So that timer only turns on when the fluoro pedal, so I should mention that too, right? Either the fluoro is controlled up where the person's hand is by the carriage or outside in a remote room, or on the inside by a pedal that's on the floor, right? Like kind of like a foot pad. And the same rules for collimation apply, right? The more skin that can not receive the beam, in other words, collimate more, field size smaller, so less radiation to the skin, the better for the patient. And you don't have to memorize these terms. Other than knowing that when we're using barium, right, we're up at around 110. When we're using ionated contrast or even non-ionic contrast, in other words, the injectable stuff, um, we have to be around 70 or 75 because we don't want to burn out the contrast. And I think just a couple more slides here. So half value layer, I believe we spoke about before in another class, right? The half value layer is the amount of filtration. So filtration is still in effect here. We're trying to reduce the longer wavelengths, lower energy photons that don't contribute to subject contrast, but do contribute to dose. by utilizing a filtration material. That amount of material that has the ability, so the amount in millimeters or centimeters, whatever you want to use, that will allow us to reduce the amount of radiation by half, the amount of intensity by one half, is known as the half volume layer. And those half volume layers, the actual amount is based on different manufacturers and different types of machinery, etc. So we can't say that it's always going to be the certain amount of centimeters or whatever unit we're using to measure. Again, safety is a concern. A lot of radiation. Best place to be is not in the room whenever possible. But if we do have to be in the room, we have to make sure that we have our lead apron. We have to make sure that we stand as far away as possible. There's not much we can do in terms of time, so that's why I kind of left that out of our discussion before, right? Usually it would be time, distance, shielding is our mantra, but we don't have much control over time. And unfortunately, I saw this a lot, right? When you had physicians who were in training, residents per se, they were just not as good, right? They didn't have the experience left. So we used to log the fluoro time, right? And the fluoro time was always higher for those people that were learning, right? So you're going to encounter students, right? Except they're going to be students or physicians in training, while you will be X-ray technologists. And at that point, you will probably know a lot more than they do. Mobile fluoroscopy, we talked a little bit about this, but you can see here's our image intensifier. It's round. We talked, I think, enough about this in the lab the other week, but essentially it's still a great tool. So I don't have anything more to mention, right? The process of image intensification is essentially the same. And that there does it for us. That was our penultimate lecture, meaning we only have one more lecture to go on Wednesday. I can't believe this is our last week. I'm going to stop recording here.